high dynamic range and what is NoGhost and how is it actually used, and what are maybe from our perspective things to consider when going to this type of application spaces. So first, maybe just a couple of very high level definitions. What is high dynamic range or wide dynamic range? Sometimes it's called standard dynamic range, and it leaves a little bit to interpretation whether you may be more on the vision algorithm side, whether you may be in the consumer space and talk about TVs, or like we are if you're in the optic space. So defining what we actually talk about is always helpful. And in the end, dynamic range is just defining a scale where you can, how much detail you can detect in one image frame, from the darkest part in your picture all the way to the brightest part in your picture that is just before maybe saturation of the sensor. And that ratio between the darkest and lightest part, right, that's your dynamic range. And ideally, you can capture in a single frame a lot of detail, and you're not like here shown in those two pictures, the typical scenes driving out of a tunnel, looking out of a house, looking into a house, right? Systems that are not optimized for high dynamic applications, you have rather an impression like on the left where you're blinded through the strong light from outside of the tunnel, but what you actually want to achieve is more a picture like you see on the right side, where you have a more detailed resolution that you can actually work with. So this is one thing just to set it out there. And then what rolls into that, right, is quite often stray light. And stray light, the way we define it, is simply light in your optical system that is coming from a source that you maybe know or don't know, but it simply doesn't follow the path that you want it to follow. So it creates unwanted noise artifacts that you have to deal with. And it might not be as challenging for a human eye, but with the growth and with the increase of high dynamic range application, we also see an increase of computer vision, artificial intelligence being introduced. And that's why stray light is suddenly also such a hot topic. And Ben, we talked about this before. And if I remember, just going back a couple of years, right, no one really cared about stray light. So why is it really such a hot topic recently?
Yeah, you're right. Several years ago, 5 years ago, nobody really talked too much about dynamic range in terms of sensors or lenses. And, sensors at the time were 40 or 60 dB. And most of the lenses on the market, if they were decent lenses, were completely fine with that. But what happened is as the sensor dynamic range started increasing to 80, 100, 120, those old lenses, suddenly you started seeing stray light artifacts and ghosts, exactly like what we're showing here on the left. They were always there. They just weren't detectable before with the older generation of sensors. So, with the new sensors, you're seeing so much more. The lenses need to be much cleaner. We use the word cleaner, free of artifacts, ghosts, veiling glare needs to be lower. So that's the kind of reason there's so much interest these days in high dynamic range lenses. And this is something that we started recognizing even before HDR sensors were ubiquitous in the market or commonplace. So this is something that Sunex has really been passionate about for at least 6 or 8 years now.
Okay, thank you. So, and you mentioned, right, it's suddenly something we have done HDR before, maybe before it was a key topic on conferences where we see now the sensors actually pushing this boundary. And we're also, we're looking into optimizing our designs for stray light. So if we really, both of them basically have to come together to align with the requirements of today, right? We see sensors are growing their range. So we have to look at HDR support for those sensors as well as reducing stray light. And I mentioned it before, right? It's sensors are getting better, and at the same time, less humans are looking at a live feed. It's more computers and AI algorithms making the decisions, right? So from our perspective, we have to start off with a lens design, and we'll get a little bit into detail what we mean with that, right? So you have to build a lens that is set up to support those sensors with what Ben just mentioned, with a cleaner image to allow high dynamic range. Again, the amount of detail you can see in one single frame that's captured, whether that is during the day, at nighttime, or maybe somewhere in between, right? How much detail can you really see in your picture? So that's a foundation. And then reducing stray light is a key factor as well. Again, a human eye can quite often glance over a ghost somewhere in a live image, but a computer algorithm might get tripped by it, right? And here's an example, right? If you envision this coming from an e-mirror, from a camera vision system on the side of the car, if you would be the human looking at the live feed, you could always see, yeah, that's kind of a reflection. But if you have, and if you allow your car to make a decision for you, the algorithm has to be able to make a decision whether this is maybe a motorbike that's just trying to pass me, or whether that's a reflection. So the cleaner image we can deliver from a lens perspective into the sensor, better algorithms will be able to deal with that. And Ben, if I understood you correctly, you just said before, right, in the past when sensors had a lower dynamic range, you might not have seen everything during the day, all the details that you wanted to resolve. But in a nighttime situation like we see in a picture, that might have been beneficial because a lot of noise that we can see now wouldn't simply have been resolved, wouldn't have shown up, right?
Yeah, that's true. You know, obviously having more dynamic ranges is a good thing. It allows you to detect things that otherwise might not be detectable, but kind of with the good comes the bad. You know, also all of these ghosts and so forth are now also detectable. So that's just what makes it all the more important that the lens be clean, so that there isn't the kind of mistake. Especially, you know, a human might look at this image that we're showing here and say, oh, yeah, of course it's a ghost. You know, I've seen 2001 and Star Trek, and I recognize what a ghost looks like. But an algorithm, you know, doesn't have that kind of discerning ability. And so what might look like a ghost could also appear as a motorcycle or another car. And, you know, obviously that could have catastrophic consequences to your application.
Mm-hmm. So again, we now established that, right, we can't really look only at one side of the coin. We have to look at the foundational lens design to support HDR application. And then obviously we also have to make sure we use our technologies that we kind of summarize under NoGhost to optimize the stray light performance. So let's look at those a little bit individually. And everybody who's a regular attendee for our webinars should by now know that we like those Venn diagrams. So I used one here as well, just to bring it again together. So on one side is obviously the lens design. This includes the optical design, the mechanical, the optomech design, the coating design, right? All of those are the initial thoughts that you put into these are very crucial to designing a high-performing lens in this space. And then having the appropriate simulation tools to maybe be able to use light tools to visualize and investigate stray light performance and those kind of things. And what is really, really important to understand the capabilities of your own manufacturing process, so that you design with the manufacturing process in mind. And that also brings me to the second one, right? It's not just design, it's a design process that spans from the initial design where you maybe started off with a blank paper all the way into the actual capabilities of bringing it into a product. And that includes the fabrication capabilities of making, for instance, the glass or some of the molds. It includes your R&D capabilities of building early prototype, material know-how. And then again, if we do this in the millions a year, making sure that you have a very strict and rigid incoming quality control to make sure that the initial design performance and the initial build performance can be continuously delivered in time and in the quality needed. And then obviously getting the customer's feedback about the performance of the lens in the early stages is very critical. Ben, there's two things in here: material know-how and right, also then using incoming quality control to kind of monitor on that. Maybe you can speak a little bit to how selecting the right materials is important from the beginning, and then maybe how material over time, right, could impact also HDR and stray light performance.
Yeah, I think this is a good point to talk about this briefly. I think there's not so much a misconception. I think there's a understanding in the market that for high dynamic range lenses, you know, coating is very important. A lot of people think, oh, you take a lens and you put better coating on it. And that's not incorrect. The coating is a big part of light control in high dynamic range design and manufacture. But it's so much deeper than that. You know, different, as everyone knows, the refractive index of glass is a function of wavelength. And so we'll talk a little bit about this more later in the hyperspectral section, but What this means is that you need to be concerned about high dynamic range over a broad band. And so broadband coatings are important, but also the materials you choose, like anodization, like surface roughness, all of these have different effects on different wavelengths. And they need to be picked according to the use case, the field of views you're dealing with. F number has an impact. You know, a wider aperture allows not only more light, but higher angles. And so the choice of material, not just coating, becomes critical. And so we look at this in the design phase, but also in production and in test. We look at the reflectivities of the materials, the shapes, the scatter off of different elements. And then going forward in mass production, you also have to monitor this. It's not something that you fix once and then you hope it stays good. These things need to be monitored. Cleanliness is very important. So you could have a very clean, great optic, and then if there's any contamination on it, that's a potential issue. So it's really an ongoing process from beginning, meaning design, all the way to final QC to make sure that all of these different aspects that influence stray light are under control at all times.
You had a couple of good keywords already. That's a great segue into the third part of this diagram, the manufacturing process, right? You just mentioned already the manufacturing facilities, right? The clean room level facilities that you require and today to really build this type of lenses, right? It's not only because the sensor resolution in general is going up with smaller and smaller pixels, but the expectation in terms of stray light performance and HDR performance is going up at the same time. So there's multiple challenges which require a manufacturing facility to really be a clean room facility to avoid contamination as much as possible, just as one of the aspects, right? And then
Absolutely.
You're already addressing testing systems, and the test systems, again, it kind of rolls a little bit into your design verification and R&D capabilities, but also being that this needs to be reflected in mass production so that every single lens can be in production at an end-of-line test to be actually tested against certain requirements. And doing this again in high volume is what is our core expertise here. And then you already mentioned outgoing quality control, making sure it's tested, it's in high volume, and it has the quality that our customers are requiring. And then one thing that's still left in this diagram, which is important for us, it's a continuous learning process. It's just not 1 + 1 = 2, right? What in this type of application space, for high dynamic range and NoGhost, no lens is the same. So we always learn, we always gain new insights, new knowledge based on the latest design we did, and we try to bring that back into the next design iteration to learn from it. But eventually, quite often, you kick off this process again and again. But obviously, building experience and knowledge over time is very helpful here in this overall process. So looking now into HDR optimized a little bit more in design expertise, what does it really mean, right? And there's, again, if you're someone who is maybe designing lenses, or if you're someone who is using lenses, right, and ask different companies to maybe build and suggest a design for your requirements, you will never come across something where two designs are exactly the same. So what are benefits of one over the other, right? Assuming they all achieve performance. What we typically try to do for various reasons, and we have done some samples and we see that confirmed quite often, is that we basically believe is if you have less elements in there, that has a benefit, right? There's an obvious benefit in terms of cost, less material, less elements, but there's also other benefits which actually lead into the topics we're discussing today, right? And you see a couple of examples here. If we're not taking effects in off-barrel material or spacer material, just simply reducing the number of elements by one inside an optical stack can heavily reduce the number of parasitic images you have to deal with, and you eventually have to optimize for it, right? We're currently seeing here the comparison between like a lens on the left side with 9 and on the right side with 8 elements. There are lenses with like 10, 11, 12, 13 elements, right? So if you take those formulas and use that for a lens with 10, 11, or 12 individual lens elements, and you can reduce just one element, right? You're shaving off hundreds, if not thousands, of parasitic images that can cause unwanted artifacts and noise in your system. So trying to design for less elements again, always in achieving performance is kind of a criteria we're trying to achieve. And Ben, is there a break even, right? We quite often say, oh, we need maybe an additional element to achieve a certain performance spec, like to correct for chromatic aberration or something. But at the same time, we don't want to have another element because you simply have two surfaces more where something can bounce off. So, so where's the trade-off? Where's the ideal scenario?
Yeah, interesting question. There probably isn't a one-size-fits-all kind of answer to that. I think in general, we talk about Sunex, having elegant designs, which is what you're talking about. And in general, we don't ever want to use more glass than is necessary to solve the problem at hand. We also don't want to be, austere. We don't want to sacrifice image quality either. So you do need to use as many elements as is necessary to meet the other performance requirements, particularly things like MTF and relative illumination and field of view, those first order kind of requirements. But beyond that, we see a lot of, companies out there who kind of throw glass sometimes at solving an image. Adding more glass can increase the MTF, but it comes with heavy penalties and not just stray light. There's also things like transmission, total transmission, and cost and complexity. So our philosophy is this elegant design principle where we use enough glass to meet or exceed the requirements, but no more glass than is necessary. And the balance there is really kind of an art form, and it's one of the things that we excel in, is finding the right balance. And I say it's not a one-size-fits-all because every use case is different. Some use cases are hypercritical or hypersensitive to stray light. Others want to emphasize MTF. So finding that balance is really the core of what we do.
Okay. I just in parallel, I was monitoring our Q&A in there, and apologize if I use certain words that you may be not used to or use different acronyms. So just for clarification, when we talk about lens elements, that is referring to individual elements inside the optical stack, right? If you think about a lens as a combination of a metal barrel or a different material barrel and individual glass or plastic elements inside, that's when we talk about a lens element. So that's the individual element you would see if you would cut open a lens barrel. And again, there are quite often more than one required, depending on the requirements that our customers are putting to us. We do have individual elements as well in our portfolio, but that's very, very small applications where you maybe can live with a single element to achieve the performance you're looking for. And there was another question in the Q&A as well, where there's maybe additional material around this topic of HDR. And I'm more than happy to look up some of those and send them then later by email to you. Mm-hmm. So please keep using the Q&A if you have individual questions. It's very helpful because typically if one person is thinking about that, someone else might have as well. So the answer is always helpful to others as well. Ben was already touching earlier on hyperspectral, right? And where HDR is, again, is the definition to resolve a lot of detail from very light, very bright to very dark inside one frame. Hyperspectral is defining or talking about having a very consistent performance in terms of, for instance, MTF, lateral color, and other key parameters for a lens across a wide spectrum. Not necessarily tied to HDR, but the challenge of doing an HDR-optimized lens becomes so much more if you now have to do that over a very, very wide wavelength band. And Ben, maybe you can point out, and I think you were already picking up on one or two of those before, but what are really the challenges if we something that we optimize for the visible space, we now get asked, oh, I really like this lens. Can't you just make it hyperspectral and allow me to go from 420 all the way to 940?
Right. Yeah. Yeah. You were touching on it earlier. Trying to control stray light over a limited waveband, like let's say visible, is challenging enough. But the simple fact is, when you expand that wavelength range from visible through the infrared, I mean, for one thing, there's simply more light that you have to deal with. And then, as we discussed before, that light that over that band is also dependent. The wavelength interacts differently in terms of the design itself. So index of refraction being a function of wavelength. So you've got all this light from across the band that you're trying to, first and foremost, make image, properly where you want it to go. And so on top of that, the other materials in the lens react differently to different wavelengths. So you can think about anodize as a good example. Something that might look completely black in the visible may have 20 or 30% reflection in the near infrared. So it's not only a problem of managing much more light, but light of different nature almost. And so you need to look at the whole system over the entire waveband, and it just makes it that much more challenging. So the problem is definitely solvable, and we do have hyperspectral lenses in our portfolio and online that have high dynamic range performance from the visible all the way through the NAR, but it's obviously a bit more challenging than a limited waveband application.
Yeah. So it really sounds like, right, having the dialogue with the customer is really key to really understand not only, oh, there's an NIR light source, but really what's the nature of that light source, how is that light source maybe behaving over temperature, how is the wavelength changing, and those
things. Yeah. Yeah, and again, this comes back to, there's not a one size fits all when it comes to HDR. We can and do have lenses that are high performing in terms of HDR across the visible or across the IR or across the whole band. But it's always good to talk to the customer and understand the specific use case, because there may be things that we can do, or there may be cases where the customer doesn't need and maybe is giving up a trade-off for something that they don't need to give up a trade-off for. And we can help understand and optimize for those use cases.
Yeah, I think trade-off is a good point, right? Typically, nothing comes for free, right? What I noticed, and that's maybe again a good segue for the next slide that I have here, when we move now from HDR a little bit to NoGhost, optimizing for stray light. I think what I notice sometimes when I talk with my clients is when we talk about coding and filters. Sometimes, right, if we look at filters, maybe first on the right side here in that slide, right, quite often we have an application that's purely in the visible space, and sometimes we have applications which are purely in the near-infrared space, right? In automotive, quite often we see maybe driver monitoring applications centered around 850 and 940 nanometer. And then we have the applications which touches a little bit hyperspectral, right? It's not going through the entire band continuously, but you have a dual bandpass situation where you want to have a nice lens performance in the visible space during the daylight, but then you want to still continue monitoring your driver during the nighttime, right? And either you're trying to use the ambient light which is left, or you have an artificial light source around one of those center frequencies. And what I notice quite often is that people tend to look at them separately and say, oh, I would like to have this performance over here in visible, and then I would like to have this kind of performance in the near infrared. And I think it's always important to bring it back to that. If we design coding, that coding recipe goes on the entire lens element, right? We don't have a portion in that lens element that's responsible for visible and another portion that is responsible for the near infrared. So if we design a coding, the coding will always be on the entire lens element, on the entire surface of that particular lens element, or both surfaces. So we always have to optimize for both, right? We can't really lock in one and say, and now we optimize the others. Whatever we do have an impact on the other side as well. And I think this is when you spoke about trade-offs, right? Am I correct there?
Absolutely, yeah. Coding, more than almost anything else, is a direct trade-off. When you try to get broader bands, there's impacts to other aspects of the coding, like transmission and off-axis reflectivity and things like that. So this is, again, a situation where there's almost an unlimited number of solutions, but it's best to talk with Sunex about what best fits your particular use case, because there really are a lot of options and a lot of things we can do.
Yeah, and right, again, what we said before, right? We every time we build a new lens and we get new customer feedback, we learn and we put that into our portfolio to, right, kind of getting a head start for the next lens we're building. But in the end, every lens is a little bit unique in performance, in the geometry, curvatures, radius, so that we always try to get very close with our nominal designs, but eventually there's always slight differences, right, that you have to be prepared for and account for and then optimize for.
Yeah, and like we talked about before, use case is extremely important. You know, things like what kind of light source, is it mixed? You know, when I say mixed, I mean visible plus infrared, or is it going to be one or the other at any given time? What kind of filters do you want? Are they switching filters? Are they passive filters like what we're showing here? You know, what kind of things are you looking for? Is there going to be, you know, is it going to be a fast exposure? Like, is there motion, or can you tolerate a longer exposure time? So all of these considerations roll up into the things which, if you joined our customizable webinar last week, you will recognize some of these things are customizable. A lot of them are, in fact, and some of them aren't. But things like codings and F numbers, that's all stuff that we can customize. And so if you contact us, we can talk these things through, and we can really tweak the lens to your specific use case.
Yeah. And then, right, we talked a lot about the optical surfaces now, right? But there's, again, inside the lens, there's so much more, right? And basically, they all impact the performance parameters that we just discussed, right? And in the end, you really have to consider, when you optimize, every single surface, every edge that's inside the optical path of every single item, right? And the goal is really, when it comes to optimizing for straight light, right? Typically, you want to reduce all unwanted reflections in your system, right, to make sure you bring the straight light performance to the level that you need it. And typically, there's some boundaries around it, right? Cost, time, and manufacturability, because it doesn't really make sense to find the perfect thing if it takes me 3-4 years to polish it or to do it, right? And if you just consider like a single ray pass hitting a single spacer in a particular angle, right, what can happen to this? It can maybe be reflected back out of the lens stack. It can be reflected further into the lens stack. It can be reflected to an element's surface that it bounces it back. It can be scattered. So there's so much to it. And since cost and time quite often is a key parameter also when we talk about a project itself, right, from a customer's perspective. But how do we balance this? What's really the key to get this right?
Yeah, you know, the thing is, as with any engineering discipline, there's a lot of things that are possible in theory, as you alluded to. Our job at Sunex, being a mass production, high precision optics company, is balancing that. I think in the very beginning, you said something about working on a lens for 3 years to launch into space, you know, 1 or 2 times. Much different problem than trying to make lenses which are high performance at, you know, quantities of tens of millions per year. And so we need to look at what is mass producible. And so this starts with the design, but you need to be able to implement it as well. And so good design is obviously the genesis of this, and then good material choice and good process monitoring, we find, are the keys to this type of thing. But based on experience and the tools that we use, be it optical design or mechanical design or straight light analysis, allow us to look at each individual element, not only as an individual piece, but also how it goes into the assembly as a whole. And like you said, there's, you know, 10 different things that can happen with this one yellow ray that you drew, and then you multiply that by thousands of rays, you know, or, you know, in theory it's millions or billions, but for the purposes of analysis, you know, it can scatter, it can reflect, it can back reflect multiple times. So each one of these elements becomes very critical in and of itself, as well as in the assembly.
Yeah. And this is maybe also good to explain a little bit when along the design process, right, the development cycle of a lens, where the times when we can interject to still optimize, right? Because it's already difficult and challenging enough to go from a theoretical design, from a nominal design to the first build, right? but it's good to understand of what options we have to keep optimizing, because typically it's not a one and done, right? And if you look at the standard development process, right, from an initial requirements and design reviews we get the design freeze. So we say, okay, that looks good. The nominal design is frozen. Let's start building something, right? This is definitely the first stage, requirements, design reviews, where we look at an HDR-optimized lens and also already reviewing the Ghost performance. But then I think building the first samples, right, inside R&D and doing design verification. This is another part, right? We just saw on the slide before. We maybe talk about material surface properties to optimize for one or the other, right? To reduce, for instance, stray light. But then I think it's really key to bring the first samples to the table, bring them to the customer so that the customer can actually do their own tests and measurement and bring feedback in that, in addition to our first article inspection report, right, hugely informs of what maybe needs to be fine-tuned another time before we go into the B sample phase that then will go through reliability testing and further down the road until we had SOP. What is also maybe worth to mention is stray light is something that is not really defined as a whole, right? Ben was mentioning before, it is something that rather has been coming up over the last couple of years, and there's not a lot of standards around it. There's one or two subcategories like veiling glare and glare spread function that are already defined by an ISO norm, but everything else that we talk about, like a clover leaf, a ghost, other artifacts, they're all not defined. So a lot of that is kind of subject to the application it has to go into the observer, and that can be two different people inside one company, that can be from us to our clients, or it can be the client's client, right? Whoever is in the end the person who is maybe using the final camera, they all have their individual kind of understanding how much of maybe a stray light is acceptable or not. Whether that is an application that is viewed or analyzed by an algorithm is important. And then obviously even having kind of an alignment and understanding how the test setups in those different companies are functioning, so that when we talk about certain stray light results, we know how they correlate and relate to each other. Again, it's a topic that is evolving in this industry, and it's not very well defined. So there's no really I'm right and you're wrong. It's really understanding how results correlate to each other to then understand how much of an improvement maybe has to be done. And again, right, Ben, tell me if I'm wrong, I think really building prototypes, seeing it actually in action and having the customer evaluate it is really key to optimizing.
Yeah, super important. And to your earlier point on this slide, you know, there really is no ISO standard for the majority of stray light artifacts and or phenomenon. And I think some people think, well, how can that be? You know, why is it so hard? You know, why can't they put an ISO spec on stray light? They, you know, like they put an ISO spec on everything else. And the classic kind of example is, well, you know, what's better, a dim spread out ghost or a very, very tiny but exceptionally bright ghost? And depending on the application, it might be one or the other. So it's very difficult to say, well, a ghost this big is failing or a ghost this bright is failing, because sometimes, you know, it might be big, but it's not objectionable. In other cases, if it's very isolated and small, even if it's very bright, it might not be objectionable. So your point about how it really depends on the use case, and that brings it back to your question, which is, you know, customer feedback is extremely important because we are the optics experts. We're not the experts in your particular application. So we need to understand what is it about your application that you're trying to accomplish. And we can design or optimize, if there's an existing lens, to that requirement.
Yeah. So maybe, since we talked about stray light, and to wrap this up a little, just giving a couple of examples why it's maybe so difficult to align on a definition of what is good, what's good enough. First here, a shameless pitch for like a video we have online. This has been done some time ago. There were basically two cameras mounted on the side mirror of a car. One was a, let's call it standard lens, and the one lens that is optimized for very low ghost. And through this drive-through, you can actually see the side-by-side comparison between the two. But to what Ben was just mentioning, right, there's some application where you maybe don't have to go the extra mile to optimize for stray light performance because the application doesn't require it. And you see very nicely in this little video where if you maybe have the sun right behind the car, it's a different situation than you drive into the sunlight, and you will suddenly see the side-by-side comparison when suddenly an optimized lens has a better performance. So it gives a good insight into when is it maybe relative and when not. But it's also, there's so many different types of ghost that can show up, and we start seeing those ghosts now more and more because we mentioned in the beginning, the sensors have now an increased dynamic range. So those things start to show up. The fact is, most of the time you can never completely reduce it. You maybe just get to the point that the sensor is not picking up on it anymore, but you still will have some level of noise. It's just a matter of time until we maybe pick up the next level. And the message is basically in this slide, you can optimize for ghosts. You can also reduce a lot of it. You might still have to look at the system level. There might be other components that can introduce noise into the system that's not necessarily pointing back to the lens that can improve this. And then it's really a matter, if you look at the example in the bottom right corner, right? It's just sometimes also to bring it to an acceptable level. Again, that it's maybe pleasing to the eyes of the observer, but also that computer algorithm and artificial intelligence system has enough chance to process those pictures and is not disturbed by that. So it's really, I think, it's to bring that home one more time, the dialogue between us and you as a customer, and having an open dialogue, understanding when a concern is a problem, but also having an open dialogue about how good is good enough, maybe put a little bit more buffer on it, because in the end, it's also key to stay in the cost and timing requirements that every given project has. So how many lenses do we have now that fall into this category, right? And you quite often, again, the first attempt is to find an off-the-shelf lens. And how can you find now off-the-shelf lenses at Sunex? And that give you kind of an idea that they are HDR optimized and low ghost. So if you go to sunex.com and in the search bar, click on advanced search, or if you're already here looking for different part numbers, if you look for keywords, for instance, if you just simply type in HDR, this will search over the lens description and it picks up HDR. And there's several pages full, and this is actually, I just reduced the screenshot. So there's 3 pages full of lenses that are titled in here with HDR. You also see at the bottom right corner, if you have a data sheet from Sunex, quite often in the lens description, again, and a little bit more text description there, you will see that it's either HDR performance lens, HDR optimized lens, or a lens we recommend for demanding HDR applications. And the graphic in the top right corner, I was just plotting as one of, like, showing you a little bit of map of the available products there. You have on the x-axis, you have the F number, and you have on the y-axis the full field of view. So you see there's a lot of lenses available going from f1.6-ish to below f.3.0 and all the way up from 20, 30 degrees, maybe a little bit lower, to way over to 100 degrees. So there's a huge portfolio of lenses that are already available. And what we already mentioned in our previous webinar about customization, it's always good to find an off-the-shelf lens that is delivering on 1 or 2 of the important vectors that your program might have, so you can do an early evaluation of something off the shelf. You can start your first test and then take it from there. Because again, the dialogue between us and you is very, very important. And if you can start off with maybe even 2 or 3 different off-the-shelf lenses, where one lens you pick to kind of investigate a very, very good stray light performance, and then you pick another lens that maybe is more beneficial to your field of view. Those tests on your side are very, very informative for us, where you say, you know what, I really like the stray light performance of lens A, and I really like the MTF performance of lens B. Can we build a custom design that brings those 2 worlds together? That's a really important guideline for us, so that we really know what to design for. What are the specs beyond specs you put in an Excel sheet, some measured specs and experience you have with actual samples is very, very helpful for us to define the boundaries when we design lenses. So again, like we did in the other webinars, we're really thankful for you spending your time with us today. You have here in the slide as well myself and Ben's direct contact. Feel free to send us an email. Feel free to also go directly to our main email address. And what we're really looking for is to use this webinar kind of as a stepstone, as a primer for you to understand better how we think about this topic, maybe get a little bit of an understanding about our capabilities. And then we just hope to have this dialogue for you to take some of our off-the-shelf lenses, see how they already fit into your needs, and then see what we need to optimize and customize for your specific requirements. Ben, do we still have questions open in the Q&A session?
Looks like everything has been answered, but if anybody has any questions or if we didn't answer anything thoroughly enough for you, go ahead and shout out via the Q&A.
And I think as always, Ben and I will stay on for a couple of minutes longer to see if there's anything coming in. But this concludes the official part of the webinar. Again, thanks for your attendance, and we're looking forward to talking to you about your project. Thanks
Thank you, everybody.